Okay, guys, we're going to start with the next talk. Here with me on stage is Kilian Glas. He's going to talk about modular blockchains and data availability. He's a PhD student from Munich at the Technical University. And yeah, I'm looking forward to the amazing talk.
Thank you very much. Okay, perfect. All right, yeah, I'm as I already announced, I'm a PhD student at the chair of Network Architectures and Services at TUM. And yeah, today I want to talk about, briefly give a brief introduction about modular blockchains. First, this is a kind of a very brief overview. This is a complex topic I could talk a lot about. So yeah, this is merely meant for you to kind of get a brief idea about the general approach, let's say. And then in the second part of the talk, I want to go a bit more into detail about one specific layer of the modular stack, so to say, which is data availability. And there we'll talk specifically about data availability and data availability sampling and how it's envisioned to be implemented in the upcoming scalable data availability layer of Ethereum, which is dank sharding. Okay, so let's first talk about conventional blockchains. So in conventional blockchains, we can roughly decompose our blockchain validator nodes into three layers, namely the consensus layer, which is where the agreement on the order of transactions and the order of blocks happens, and also where blocks are finalized such that they cannot be reverted later on. Then we have the data availability layer, which is kind of implicit in normal blockchains, let's say. This is basically guarantees that all transactions are available. And this allows us in conventional blockchains to validate the full block history and to get the full block state. And then we have the execution layer. That's where transaction processing happens and also where the state is maintained. So on Ethereum, this would be the EVM. All right, and those conventional layer ones or conventional blockchains like Ethereum are monolith, meaning that they provide the functionality of all of those layers, and those layers are tightly coupled. So there's a tight interplay between them. Let's have a very high-level overview how this interplay looks like. So in the first step of a let's say round, a block proposer takes a bunch of transactions, bundles them into a block, which is of course part of the consensus layer. Then in the second part, the block proposer publishes the full block into the network, and all of the nodes, all of the validator nodes download the block. And in the third step, validators execute transactions and then validate the state transition. And if that's correct, if all transactions are valid, then in the last step, they would basically, depending on the consensus protocol, they would, for instance, vote for the block. Okay, now if we look at this from a scalability perspective, we see that the data availability, downloading the block, and execution is on the critical path. And validators need to download and process the full block. If we want to scale, if we want to increase our transaction throughput, we need larger blocks, so we need more transactions per block, and therefore we need to download more data and we need to process more transactions. And this, of course, means that if we want to scale, we need to vertically scale up our validator nodes. Hence, we need to increase hardware requirements on validators, which is somewhat undesirable with respect to decentralization because it higher or increases the threshold cost, let's say, to enter the network. And then also there's, of course, some upper bound to this. We cannot infinitely scale hardware, except, I guess, we would do some parallel validator approach or something like this. And if we look at approaches like execution sharding, which have been looked at in the past, I guess, they add significant complexity to the protocol. And yeah, so we want to look at a different approach to scalability in this talk. And here the idea is that we disaggregate our layers. So in modular blockchains, we have kind of specialized individual blockchains for each layer. And then the advantage is that those specialized blockchains can be scaled independently, and yeah, developers then can essentially pick for their rollup, let's say, the stack they want. And yeah, what you've already seen here is that essentially we have now a new layer, which is a settlement layer. This is optional for modular blockchains, and that's something we do not have on standard layer ones. And that's a layer where dispute resolution happens. So I think we've seen rollups in the last in the talk before me. That's basically where, for instance, fraud proofs get resolved. Okay, now here's some very simple modular architectures, which is actually rollups or ZK rollups and validiums. And that's kind of, I guess, the simplest thing you can do. So here the idea is, I guess, as I said, you've already seen this in the talk before. We have rollups. Rollups have some form of sequencer that bundles together transactions and batches. Those batches are then compressed somehow and then are submitted to layer one. And together with the batches, we would also submit, in the case of ZK rollups, some validity proof that the transactions included in the batch are actually correct or valid. And this allows us to scale in a sense that we don't have to execute all of this, and also batches can be compressed. And in the second approach in validiums, the idea is very similar, except that we now have a data availability solution that lives off-chain, which is a data availability committee, which is a bunch of nodes that essentially post a commitment or submit a commitment to the blob data to the layer one, and then also sign this. And if all of them sign this, then we essentially on layer one we believe them that the data is available. And this allows us to scale this data availability committee outside of the layer one. And there we already see this kind of, in this very simple setting, the advantage of modular blockchains. Of course, note here that this comes with a security downside, because we have to have an additional trust assumption into this data availability committee. Okay, and yeah, I guess that's not really visible, but the architecture, of course, is very similar for optimistic rollups and for optimiums. The only difference is that we have fraud proofs instead of validity proofs. All right, now on the previous examples, the layer one was used for consensus settlement in both cases, and for the rollup architecture also for availability. Here's a kind of a small note. Usually in conventional and monolithic blockchains, the full ordering happens in the consensus layer. Here we have this additional nuance that rollups have their own sequencer. And there are multiple others, so those are just the very, very basic modular architectures, I guess. There are multiple other potential stacks. So for instance, there are sovereign rollups. There the idea is that we use a specialized data availability layer one like Celestia, which basically only provides blob ordering and data availability, and we do not have an external settlement layer. So the validity proofs are submitted to the peer-to-peer network of the sovereign rollup itself, and this allows us to be independent of a layer one smart contract. All right, now with that being said, we now want to shift our focus a bit to data availability and dive a bit deeper into what that means, since it's a very crucial aspect of the modular stack, and it's something that's probably new to you when you are when you just started with blockchain, I guess. So as I already said, as a small recap, in monolithic blockchains, data availability is rather simple. We have a very naive approach. We just download everything. And once we've downloaded everything, we can be sure that the data is available in the network, because we have all the data, of course. In modular blockchains, what we've seen is usually the execution layer is provided by rollups, and the question is, why do we even need data availability for rollup? And the second question is then, how can we build a specialized data availability layer that is scalable, so that scales specifically beyond the capacities of one node? So we don't want to download everything, we want to download only a small part of the data, but still be kind of sure that the data is available in the network. And yeah, so that's what we're gonna look at in the remainder of the talk. So a small recap on rollup security. Rollups essentially require two things for security. The first one is some way to prove that the state transition is correct. This can either be fraud proofs in optimistic rollups or snark-based validity proofs in ZK rollups. And yeah, the second thing is some way to make transaction data available, and that's data availability. Yeah, and for the remainder of this talk, we will focus on rollups on Ethereum, since that's kind of the simplest setting. Okay, so the question is, why do we need data availability in rollups? In optimistic rollups, this is rather obvious. Remember, in optimistic rollups, what we want is we want to be able to check all of the transactions such that we can find potentially fraudulent transactions. And of course, if we don't have the transaction data, then we cannot find such transactions. For ZK rollups, the story is a bit different, because for ZK rollups, we have this validity proof. So just from looking at the commitment to the rollup batch and the commitment to the state before and after, we already know that everything is correct. So why do we need transaction data in this setting? And here the thing is, we do not want to rely fully on a potentially centralized rollup operator. So for instance, if the operator becomes unavailable or becomes malicious somehow, then we want another operator to take over the rollup. And also another aspect is that we need the actual state to be able to escape from the rollup in case the operator becomes unavailable, as I said, or censors us. And therefore, we need some way to be able to reconstruct the transaction state. And here we have essentially two different options. Either we can store the full transaction data on layer 1, the full transactions, or we can store state diffs. And okay, now let's have a look. By the way, here when I say full transaction data, that actually the transaction data can be very much compressed. So it's, even if we don't have a scalable data availability layer, it's already way better than just posting transactions to layer 1 with respect to space, let's say. Okay, so how does data availability look like on Ethereum today? In March, the Denkun fork went live, and the Denkun fork introduced proto-dunk sharding. In proto-dunk sharding, the idea is that we have this concept of blob carrying transactions. So to each transaction, we can append a blob, and there's some maximum amount of blobs that can be included into a block. And the transaction itself only has access to a KCG commitments of this blob data. And blobs are pruned after 2 weeks. And compared to the legacy method, which was kind of a hacky way to do it, where blobs were included in transaction call data of a transaction, the fees for blob storage were reduced massively. Now, this still requires validators to download the full data, so that's still not kind of the end goal. What we wanted, we want to have something that kind of scales horizontally. Okay, so as I said, proto-dunk sharding does not scale beyond the capacity of a single validator. What we want is a scheme where the data is somehow distributed in a network, and we can download only a small fraction of the total data and want to be convinced that the data is actually available in the network, whatever that means. And this follows this kind of standard approach in blockchains, which is don't trust, verify. So we do not want to trust a committee, for instance, of validators that vouch for the availability of the data. And this, of course, seems to be a contradiction. Like, how can this be possible? And the solution, so this is possible, and the solution to this is data availability sampling, which was originally introduced by Al-Bassam et al. In this paper, I think from 2018 or something. And yeah, so let's look how this can be done. So if you wanted to build a sampling scheme, we could start kind of very simple and simply say, okay, the block producer publishes this large binary blob. Remember, this is really just blob, so just some bytes. There's no, let's say, structure in this, at least some structure the block producer or those verifiers care about. And in a naive approach, you would just say, okay, I pick some random indices, give me the data at those indices. And when I can download everything, then I'm convinced, basically. Now, this doesn't work. The issue here is that, let's say there's just a small chunk of data that is missing. And of course, if we look at the sampling scheme, the probability of hitting exactly this chunk is very small, specifically if the block gets very large. And this chunk, of course, could contain, let's say, a transaction that prints money or something. So the error in this case is not acceptable. And the question is, can we do better than this? Can we improve the scheme? And here the idea is, yes, we can, and we can, what we use is erasure codes. Now, as a small recap on erasure codes, the idea is basically we take, how does this work? Okay, so we take our initial data of size k, then we append some parity data here, and later on, only k out of those n total blobs, chunks are required to reconstruct the full data here. Yeah, that's a common technique that's used all over in computer science, I guess. And a specific instantiation of such a erasure coding scheme are Reed-Solomon codes, and the idea is in Reed-Solomon codes that we interpret our chunks as points on a polynomial, or basically we first interpret them as elements of a finite field and then as points on a polynomial, and then we interpolate a polynomial through those points. And if we have a polynomial of degree k minus 1, then k points are enough to reconstruct the entire thing. So the parity data we get here are simply additional evaluations of the polynomial. Yeah, this gives us a fairly elegant erasure coding scheme. Okay, now let's turn back to our example. How does this improve things? Now, what we do here in this simple example, we simply append some parity data. Here, that's we double the data. So our coding rate is 1/2. And now if we do sampling again, what we see is in order for this entire thing not to be reconstructible, so for the data here specifically, the block proposer would need to not publish basically 1/2 plus 1 chunks here. And the probability of not hitting one of those missing chunks, let's say this right side here, when we sample random indices, decays exponentially. So it's 2 to the power of minus s. Therefore, if we increase our sample size, we quickly get to a point where the error rate, the error is kind of insignificant. So that's the general idea with erasure coding. Now there's a additional thing we need. If you think about it, just using erasure coding isn't enough. Why is that? Because I could simply send around some garbage chunks, and this would mean that everyone can download the chunks maybe, but when they later on reconstruct the data, that data would be reconstructed to inconsistent values. So the question is, how can we solve this? And the idea is we use some form of commitment, and each verifier receives the same commitment to the blob data. This is part of the block itself, as part of this block carrying transactions, and then the samples come with some kind of opening proofs and consistency proofs. Now, there are two feasible options here. The first one are vector commitments, so Merkle trees plus fraud proofs. that's used in the Alba-Sam paper and also now implemented in Celestia, for instance. And then we can use polynomial commitments, namely KCG commitments, probably the most elegant way, and those are used in Danksharding. Now, let's finally talk about Danksharding after we've introduced those basic ideas. Danksharding follows the very same ideas. It's just the only difference is basically that's a two-dimensional scheme. And it builds on already implemented things that are part of proto-Danksharding, for instance, the blob carrying data and the commitments to the data. Now, how does this look like? So what we have here is the blobs of the blob carrying data. Those come from clients here, and those clients are basically rollups. And this entire thing can be interpreted as a matrix, basically. So we have 256 rows, and then we have 4,096 field elements here. And here on the right, we can see the commitments to those blobs. So those are the KCG commitments to the blob data here. And then what we do is we perform our interpolation, and this is now a two-dimensional interpolation. So we have a two-dimensional polynomial, and we do 1D interpolation in both directions. So first for the rows, and then basically for the columns. And therefore we get this expanded matrix where all of those yellow fields are parity data. Now, the vector of signed commitments here is also a commitment to this whole polynomial due to the properties of KCG commitments, basically. And the smallest unit of communication here is called a sample, and this consists of 16 field elements, and we can also aggregate the proofs for those samples together. So we only need one proof per sample. And now for reconstruction, essentially we can, if we have 50% of a row of a column, we can reconstruct this row. So for instance, we could reconstruct this row, and then we could go on reconstruct this row, and then let's say if we have enough data here, then we can reconstruct those columns and so on and so forth, and then later on we can reconstruct this, for instance. All right, so that's the basic idea, and now the question is, what's the minimum fraction of data the attacker has to withhold for the data not to be available in the network? And that's basically now a bit different. So in the worst case, the attacker could withhold all of this data, so roughly 75% minus some error of the data is available, and these other things are missing. So here the scheme differs a bit from the naive approach we showed, where the error rate or the missing parts were basically 1/2. Now, so far we've not talked about how this encoded blob data is actually stored in the network and how validators use sampling. We wanted, as we said, we only wanted to store them a small amount of data, and we wanted that they are convinced after they've downloaded the data that the data is available. So in Danksharding, data is stored. Each validator basically downloads two random rows and 2 random columns. And this means that currently, let's say in the network, there are always 5 to 10K validators. And this means that the data is available with very high replication factor. And then in addition to that, we perform this random sampling we've already seen. So we pick some random samples and we download them. And the question is, why do we need this? So this additional sampling, as I said, the coding rate differs here as opposed to before. And the problem is, if we would only download the custody rows and columns, then we would get this kind of significant error rate. So we would actually be able to, in expectation, trick 6.25% of the validators. And this would have a negative impact or may have a negative impact on consensus. So for instance, cause reorgs. So that's something we want to avoid, and therefore we use this additional sampling where we get this error rate, where validators accept a block that's actually that contains data that's not available, where the error kind of decreases exponentially in our sample size. All right, now a small note, this scheme can basically be improved a bit by using full two-dimensional full bivariate interpolation, and then we only have a kind of this yeah, we only need 1/4 to reconstruct the data. But again, that's kind of an optimization. All right. Now, as already kind of my last slide, I think. So in this talk, we've only covered the sampling and the distribution on an abstract layer with respect to the network. So as you may know, in Ethereum, there's a peer-to-peer network. And yeah, there's, of course, if you perform the sampling and this distribution of the data, there needs to be some peer-to-peer protocols in place that support this, that allow us to find samples, for instance, or that allow us to later on reconstruct data. And for distributing rows and columns, this is not too challenging. For instance, we could simply say, okay, we have a gossip subnet for each row and each column. For the sampling, this looks different. First of all, there's some efficiency issues. For instance, if we use a distributed hash table and we just perform lookups to all of those samples, this causes a lot of overhead of the networking layer. And then also, we want to prevent targeted attacks, for instance, where the adversary just provides samples to specific validators or light clients. So this would also be a highly desirable yeah, property of such a protocol. And then, yeah, just in general, we need some efficient way to download samples, to locate samples and download them in presence of an adversary that tries to hinder us doing so. And yeah, so there's some open questions around this. This is currently a work in progress. There's a initial kind of proposal, which is called PeerDAS, which builds on the network infrastructure that's currently available in Ethereum, but there are plans to extend this in the future. All right, I think that was my talk. I guess we don't have time for questions, so that's it. Thank you very much.